With the recent release of Pokemon Brilliant Diamond and Shining Pearl, I've been thinking a lot about Pokemon. And one aspect I have just recently thought about more than typically, and found quite hilarious, that Pokeballs fit in your hand and can hold deities of time and space in them. 10-year-olds run around with them. This just brings up a lot of questions. Would Pokemon being in Pokeballs be so incredibly dense that it causes singularities? How much energy is actually being contained within Pokeballs? And then how can 10-year-olds throw thousands of pounds? How can anyone throw thousands of pounds with ease? Of course, Pokemon don't exist. And the answer can just be, well, they live in an alternate reality where insert fictional and undiscovered thing allows this. And that, fair. But I think it's definitely more interesting if we look at it from a perspective of a more real world. So let's figure out what 200 Pokédollars is really getting you. First, I'm going to make a bunch of assumptions. Pokemon don't exist. I am lazy. I can apply a bunch of assumptions here for reasons and makes the physics a little bit easier, calculations a little bit cleaner. But then you aren't looking at Pokemon in the real world, and my claims on insert sci-fi reason should be just as valid as your calculations. Our first assumption is that Pokemon are gaseous upon entering a Pokeball. Specifically, they're going to be an ideal gas. This allows us to both compress Pokemon down to Pokeball size, and it allows us to model a little bit easier for energy later on. Our other main assumption is just that Pokemon trainers are insanely strong. They can throw thousands of pounds. Very unsatisfying answer to how 10-year-olds can throw tons like a baseball. But it allows for density and energy calculations to be the focus of the rest of this presentation. By the way, if you're interested in any of my sources as to where anything's coming from, they should all be in the description. You can read through them there. All right, getting into that first calculation, density of the Pokeball. We're just going to need our total mass, total volume. Because we want to find the maximum density, we're going to use the maximum mass available to us. This means that we're going to use Copperajah as our example Pokemon. Copperajah weighs 650 kilograms, but he has the ability Heavy Metal, which doubles his weight. While you could say that a Heavy Metal like Groudon, for example, is more massive, Copperajah is the heaviest Pokemon in canon. There is not a heavier Pokemon with a higher weight / mass stat that is officially created by Pokemon. So we will use Copperajah for the remainder of our calculations. Keep in mind that 1,300 kilograms. Another side note, we only care about mass in our density calculation. So while Wailord is the longest Pokemon at 47 feet and 7 inches, or 14.5 meters, we only care about mass for density calculations, so we won't be looking at Wailord. Well, we have a couple of issues with Pokeballs now. The first one being that they change size. When pressing the button, it allows it to shrink and grow, which is great for portability. but complicates our calculations. Our other issue is that I can't seem to find an official size for Pokeballs, either large or small versions, anywhere. So to remedy this, we're just going to take two sets of calculations, one for a baseball size, one for a ping pong ball size. Why these sizes? It's what Bulbapedia said. I'm just going with that. So now that we have our volume and mass, we can calculate our density for each of the different size Pokeballs. Just note that we did assume that the mass of the Pokeballs themselves was basically 0, because 1,300 kilograms is very large, and the Pokeball's probably not within an order of magnitude of that. And it would just increase the density further. But all of this is to say, Pokeballs are incredibly dense. That is times 10 to the 6th on the baseball sized in kilograms per meter cubed. Just for some perspective, that's about 340 times denser than uranium. The ping pong ball sized is 2,050 times denser. They still don't come close to neutron stars, though. Because we know that neutron stars exist in the real world, and not as black holes, they exist as neutron stars, we can kind of wave our hands and say, okay, Pokeballs, the heaviest Pokemon in a Pokeball would not cause a singularity, so they can exist. Not super interesting. It would have been more cool if it was so dense that it caused a black hole, but it is what it is. So the next question then is, how much energy does the containment of 1,300 kilograms produce? The short answer is a lot of energy, but we're going to go through the long and boring one anyways. So remember how at the beginning I said that we're going to model Pokemon as ideal gases? Well, here's where it comes into play. We can combine the work energy theorem, work done by a gas, and the ideal gas law to create a system of known variables that we have already defined and calculate energy. So going through simplification, canceling out a few different terms, we can see that containing a heavy metal Copperajah weighing about 1,300 kilograms in any size ball, given that the volume cancels, is about 20,000 kilojoules, or 5.6 kilowatt hours. Just as a side note, real quick, we did use the molar mass of copper. I thought it was fitting because I don't know Copperajah's molecular makeup to find its molar mass. And copper's in its name. If you don't like that, deal with it. Let me repeat that number for you, though. 5.613 kilowatt hours. That means 6 Pokeballs would power a house for an entire day. And 10-year-olds buy these by the dozens and carry hundreds of them. Of course, Pokeballs aren't real. None of the numbers I really said are real other than gas constants. A ton of assumptions were made to get us here, but maybe you learned something. And even if you didn't learn anything about math or physics, then you at least learned that you wasted your time here. Thanks for watching.